Swayam Prabha. Digital India. Educated India.
As of now, the way we defined this random process, they are very general notion, right? Very abstract, general. We just said, okay, it is going to capture something. But often to model something and to analyze this, we want this random process which have bit more structure in them. So for example, when we said, okay, we said random variable and distribution. But any random variable, if I just take any arbitrary distributions, maybe it's hard for me. Then that's why we defined some special distributions, right? We said uniform distribution, then said Gaussian, geometric, different distributions which are helpful to model the reality to somewhat extent, but they are also a bit more structured in the sense we can analyze them system when we model using these distributions. Now similarly, when we are talking about different random process, any arbitrary random process, if I take, maybe I may not able to analyze my system at all. So I would like to now look for certain random process which have more structure in it, but still capture my reality. Then those using those random process, maybe I can try to understand my system and get some useful insights. Now we are going to now start focusing on special type of random processes. Okay, so we will see like today and tomorrow we are going to talk about one special random process called Poisson process, and later in the second half of the course we are going to focus significantly on a particular random process called Markov processes. Okay, now let us say Poisson process. Okay, so to define this notion of Poisson process, we have to understand two properties called some notion called notion of independent increments and another called a counting process. Okay, so let me first talk about independent increments. I mean, most of these things, like you will find or start relating these things actually when you get into modeling business and try to analyze. If you just get into just some coding business, you will never appreciate any of these things. If you want to real system you want to analyze, yes, you need all of these things. Like you need systematic tools to understand any system, and you have some common language of talking to other guys who are also doing or understand what you are talking about, right? So you need all these things. If you are not going to do any system analysis or modeling, maybe in your life you will never appreciate this, or you will never find use of these things. Okay, so what I mean by independent increments. Suppose let's say I have a process xt and I look at over an interval, let's say AB. So let's time being, let's assume that this is a continuous process. So my t is a continuous here and I am going to take some interval. Then I am going to look at this difference, that is the difference in my random variables at this on this interval. Okay, so I'm going to look at my random variable at this time index b and at the beginning of this interval at a, and then look at what happened in this. So suppose your process is like something like whatever it is, and I took this interval and I want to see that, okay, between this interval what happened. Actually I increased or decreased, whatever you want to understand. So let's say you are interested in these intervals, and now we are going to say that random process. Okay, so what we will do is, if you have a random process, let's say, and you take any n and you take n indices such that these indices are arranged in increasing order. The first index is t0, second is t1, t2 to tn. And now if you look at this differences between this interval, the first is xt1 minus xt0, then xt2 minus xt1, like that. Now if these are mutually independent, okay, what I mean by mutually independent, you understand the meaning of mutually independent. If I take this, it is independent of all others, and similarly for every point. If they are mutually independent, then I say that it is has independent increments. Okay, for example, here if I would, let's say this is my I will take another interval here, and maybe, so this is, let's say, t0, and this is t1, t2, t3, and let's say this is tn. So what if I take the increment in this and look at increment in this interval, like each of this interval, if that is going to be independent, then I am going to call this as independent random process with independent increments. So notice that these intervals need not be of the same length. One could be larger here, one could be smaller. So that's why, like, this is any set of indices, just that they are in increasing order. And if you are going to look at the difference, they should be mutually independent. Okay. So now we look at something called counting process. So counting process, as the name indicates, it does the job of counting. So for example, in this graph I have shown here, it could be like a plot of something, like the number of people that have entered at this time, and let's say nobody leaves once they enter, like so this is going to be increasing curve, and this maybe, let's say, if it is an increasing curve, so there may be like if I learn to look at this point or this point, you can think of like how many people by that time have entered or already there, and that could be like thought as a counting. So that we will try to make it more formal. So this is just like a general graph. So let's say we are going to say that a function, we actually already said this. So you take a function f which will give you at any time any positive real number integer valued outcome, and it is such that it is non-decreasing, that it keeps increasing, and it is right continuous. We already understand what we mean by right continuous, right? Such a function is called as counting function. Okay, for example of a counting function could be Let us say I am counting number of students that are arriving into the classroom. Okay, let us say all my arrival happens between 5:30 p.m. to let us say max 5:35 or 5:40 p.m. and let us say you guys enter one at a time. Okay, and then at each of this time second maybe I will have jump like this, it remains like this, maybe like this, here nobody comes, they comes, and then like this, then some people start coming third. Okay, so such a process, such a function can be a counting process, right, by our definition. It is non-decreasing and I can make it right continuous always by defining the point to be at this to be this point, and I can also make this to be a 0, yeah, at f of equals to 0. Okay, fine. So now to such a function, counting function can be represented in many ways. One possibility is, suppose I am going to denote this. Okay, this is T0, T1, T2, this is T3, and this is like T4. So T1 is the time instant when the first entry happened, or when the first count happened. So T2 is the time when the second entry happened. So I can on my x-axis I could denote my time like this, right? So whenever an entry happened, that time index I will look into, then I will call appropriately. If it is the fourth entry, then I will just denote it as T4. So then my f function can be represented in terms of this Ti's, right? So and same thing, right? Like if you tell me this exact points T1, T2 on this x-axis, I know that on these points a jump is happening, and then I can construct this function from that. So for example, like if you just tell me another thing and just tell me, okay, here, you just give me this T1, T2, T3, T4, then I know my function looks like here, here. So I could reconstruct my function. Another possibility to represent the same function is, instead of giving this time at which it is arriving, just give me the entire counting time. For example, okay, after how much time from the origin the first arrival, first count happened. Let's call this un. And since the first count, how much time it elapsed before the second count happened. So that could be u2. And after the second count, how much time it elapsed before the third could happen. This is u3, like this, right? So you could also express, I could also write this in terms of ui's, where ui's are this intercount times. Okay. So how is this ui's related to ti's? So what is u2 here? T2 minus T1, right? And by default T of 0 is going to be taken as 0. So when I set u1 here, this is going to be T1 minus T0, right? T0 is always going to be the origin for us. Okay. So the same f can be expressed either in terms of this count times or in terms of this intercount times, right? Now, so how to make this explicit? For example, if I am given, let's say I have been given this tn's. count times. How can I construct my f function from this? So I want to construct f means, so suppose let us say you have been given this time slots and I will ask you to tell me what happens to this function at time t. So give me the value of this f of t. So that means you have to basically count how many counts have happened before that, and that is going to give you the value of function f of t, right. So the formal way of writing that is indicator that t is greater than n equals to 1 to infinity. So in this case, let us say your t is here, we know that this t is going to be greater than t1, that will add 1 here, it will also going to be greater than t2, this will add another one here, this is going to be greater than t3, will add 3 here, but t is not greater than t4, I am saying they are all going to add 0 0. So here you will recover that the value is going to be 3 in that case. Okay. Now if I have only given my ft function like this, how to recover this count times? So I want to now find out Tn from my ft function. So how you are going to represent this? This is going to be minimum value of t such that f of t is going to be greater than or equals to 10. Is this correct? Try to digest this. So let us say I have been given this function ft now. From this I want to understand when the nth count happened, right? So just look, when this guy f of t is going to take value larger than n, but look at the smallest value of that t. So that is going to give me my Tn. And I already represented ui in terms of this count times, but I could also write Tn in terms of my intercount times. How can I write Tn in terms of ui's? So it will, like, suppose if I want to get T4, all I need to do is this ui's I need to add. This is ui I equals to 1 to n, right? So now coming back to counting process. So all of you understand what I mean by a counting function right now. We have already defined what is a counting function. It has to satisfy like non-decreasing property and right continuity property. And I already defined you what it means by sample path of a random process. So sample path of a random process is if you fix an omega and look it as a function in t, that graph is, we called it as sample path, right? Now what we are saying is, if the random process is such that if its sample path is a counting function, then we are going to call it as a counting process. Is this clear? So each of the sample point has to be a counting function, then we are going to call that process as a counting process. That's fine. Like you can, when we see example, it will be more clear. This is just a definition. So then we have defined two properties. One is the independent increment property, and another is a counting property. So there is one distribution what I already called as Poisson process, which is based on these properties, and it comes very useful when we want to model many things. So let me define that process now, which is based on these two properties. Greater than S. Okay, just what random process means is, for a given lambda, it is a counting process. That means all of its sample path has to be a counting function. Then it has independent increments. So if you look into difference number of counts between different disjoint intervals, they have to be independent. And third, if you look at this random variable, for take some t and s and look at the difference. So the way I defined is, okay, this should be nt minus ns. That is the random variable at nt and ns. They have Poisson distributed. We all know what is Poisson distribution, right? But with what rate? That rate depends on the length of the interval multiplied by lambda. So if these three properties holds, we are going to call this process as a Poisson process, and this Poisson process have very interesting properties which we will talk in the next class.